Okay, so now we're going to look at the total differential. And we're going to start by thinking about just a function of a single variable f of x. Okay, we think about what df by dx represents. Okay, we can write this as f prime of x. Okay, and here's our function f of x. X on the here and f of x, or you can call this y if you want. Okay, so f prime of x is the gradient at any point x. And you've been told, I guess in school, to think of this thing as one object and not as a fraction. It's not a fraction of two things, okay? It's not this divided by this. It's one object. Okay, but actually in university now we're going to tell you to think about it as two different objects. So df we can write as f prime of x dx. Okay, and this df is called the differential. Okay, and this is not the change in the function when you change x, but it's the linear approximation of it. Okay, so let's say we start with x here. This is x, okay? Then if we change x to x plus delta x, then our function changes from here to here, okay? So the change in the function is this thing, okay, delta f. But the df is actually the linear approximation. So we take the tangent at this point x, okay, and this df is the rate of change of x at this point. So this is the tangent, the rate of change of x times the delta x. Okay, so if this is delta x, then this only changes by this amount. Okay, not this amount. Okay, so df, the differential, it's the linear approximation to the change in f as x goes to x plus delta x, or dx. Okay, so that's functions of a single variable. So now we can think about functions of two variables. So let's think about a function that depends on x and y. Okay, and let's think about the change in the function, okay, as we change x to x plus delta x, okay, and y to y plus delta y. Okay, so we're looking at delta f, that's the change in the function. Okay, and it's the function evaluated at this thing, x plus delta x, comma, at y plus delta y, minus the function evaluated at x, y. Okay, and it turns out that if we take the linear terms only, this is df by dx, so it's the rate of, it's the change in x plus the change in y, so df by dy dy. Okay, where it's understood that this holds y constant and this holds x constant, and this is called df, and this is the total differential. Okay, and we can generalize to a function of more than two variables. So in general, if we have n variables, then our df, the linear change in our function as we change all the variables, will just be a sum of df by dxi. Okay, so our n variables, we're going to call them x. Let's call them x1, x2, x3, up to xn. Okay, so if we have more than 26 variables, then we run out of letters in our alphabet. Okay, so we just call them x1 to xn. So I'm going to label them with I here, and then we've got a dxi. Okay, and we sum over I. Okay, so if you have a function of 3 variables, for an example, u equals a function of x, y, and z, then df is equal to, so I goes from 1, 2, and 3. So it's df by dx1, which is just x, it's the first thing, dx, plus df by dx2, okay, which is y in our case, dy by dy times dy, and then the x3, so I equals 3, is df by dz, dz. Okay, so that's the expression for our total differential in terms of, for a function of 3 variables. So this tells us the change in our function as we change all the variables. Okay, so in the case of x and y, we change x and y simultaneously. And it gives us the linear approximation. Okay, just like in the single function case, this was the linear approximation in the change. Okay, so we only have terms that are linear in the changes in x and y. Okay, we don't have a dx squared or a dy squared, or we don't have cross terms, dx, dy, etc. Okay, let me just clean this up a little bit. So my pen was running out a little bit, so I'll just, this is df by dy, and this is df partial f by dz, dz. Okay, note that this df, this is a normal d, and these things are partial d's. Okay, these are curly d's. All right, so let's see what we can do with this. So if we have 3 variables, f of x, y, and z, if we have x, y, and z parameterized by some parameter t, so if okay, so we've got some parameter t, and as we change t, x, y, and z change. Okay, so think back to your helix. Okay, we had one parameter t, and when we changed that, that mapped out the helix. So our x, y, and z are changing. Okay. Then we can use this, we can write down the total differential. df is partial f by dx. Okay, the partial derivative of f with respect to x, normal dx, okay, a little change in x, plus df by dy, plus df by dz, dz. Okay, so I've just written out the same thing. There's 3 variables here. Okay, this means hold y and z constant. This means hold x and z constant. And this means hold x and y constant. Okay, now if you want to see how this function changes with t, then we just take a normal derivative, df by dt. We're kind of dividing through by t. Okay, so df by dx is some number, we know what we can calculate, and we get dx by dt. Okay, plus df by dy x and z dy by dt plus df by dz holding x and y constant dz by dt. Okay, so this is like the chain rule. This is like the chain rule for partial derivatives. Okay, so df by dt is the partial derivative of f with respect to x times dx by dt plus the partial derivative of f with respect to y times dy by dt plus the partial derivative of df by dz times dz by dt. Okay, so this is a useful chain rule. Okay, so let's think about a chain rule example. Let's think about a function of two variables, u equals x to the power 4 plus y to the power 4. Okay, but we also know that x is a parameter, x is parameterized by some parameter t. Okay, so x is cosine t and y is sine t. Okay, and the question is, how does this function change as a function of t? So what is du by dt equal to? Okay, that's the question. Okay, and this is where we use our chain rule. So we start with our total differential and use the chain rule that we just showed. Okay, so u is a function of x and y, and remember, total differential for a function of n variables is the sum from 1 to n df by dx I dxi. Okay, where our n variables are x1, x2, xn. Okay, so this looks intimidating, but it's just a sum. Okay, this thing with x1 plus this thing with x2 plus this thing with x3. Okay. Okay, so here our function u is a function of two variables, x and y. Okay, so our total differential du equals, and it equals partial derivative of u with respect to the first variable, which is x, okay, dx, plus partial derivative of u with respect to the second variable, which is y, dy. Okay, and these are partial derivatives, so this means constant y, and this means take the derivative with respect to constant x. Okay, now what is du by dt? How does u change as t changes? Okay, du by dt is just given by this, okay, as we saw. So the partial derivative of du by dx times dx by dt, this is a normal derivative, plus the partial derivative of du by dy times the normal derivative of dy by dt. Okay, so we need four things. We need du by dx with y held constant. Okay, so du by dx with y held constant is just 4x cubed. We need du by dy with x held constant. Okay, so du by dy implies that we hold x constant. So du by dy partial derivative is just 4y cubed. Okay, and then we also need dx by dt. Dx by dt. We know what x is, it's cosine t, so dx by dt is minus sine t. And we need dy by dt. And dy by dt is just cosine t. Okay, and minus sine t is just equal to minus y, and cosine t is equal to x. Okay, from here. So this tells us that du by dt equals the partial derivative du by dx, that's 4x cubed, dx by dt, and dx by dt we're saying is minus y, so we get a minus y, plus du by dy, that's 4y cubed, times dy by dt, which we're saying is x. Okay? And if you want to put it in terms of t, then this is just minus 4 x cubed, so that's cosine cubed t times y, and that's sine t, plus 4 y cubed is sine t cubed times x, which is cosine t. Okay, so that's an example of using the chain rule on a function of two variables.